Welcome, junior associates. Imagine you are a master detective walking into a crime scene. Most people who look at a shattered ornate porcelain vase just see a mess, a heap of useless ceramic shards. They might be able to tell you the total weight of the debris, but that's where their investigation ends. They lack the vision to see the history behind the wreckage. But a true detective? They see the story. By looking at the size of the pieces, the quote cleavage sites where the porcelain snapped, and the distance the shards traveled, they can tell you exactly how high the vase fell from, the angle of the impact, and the force that hit it. They can mentally reconstruct the original shape, the era it was made, and perhaps even identify who knocked it over. In the world of high-end analytical research, knowing the total mass of a molecule is like knowing the price of a car. It's an essential starting point, but it tells you very little about what's actually happening under the hood. The pro move, the skill that separates the elite researchers from the button pushers, is structural elucidation. Today, we are going to stop just weighing molecules. We are going to become molecular detectives. We are going to learn how to look at the scrap metal of a mass spectrum and logically reconstruct the original chemical identity. This is where the data stops being a list of numbers and starts being a real chemical truth. Let's learn the rules of the break. In my experience, the biggest mistake beginners make is thinking that molecular fragmentation is a form of random chaos. It isn't. Molecules don't just explode like a cinematic special effect. They break according to the strict laws of thermodynamics and structural stability. In our interrogation room, we use specific forces to induce these breaks. We've previously discussed collision-induced dissociation, CID, and its high-energy cousin, HCD. Think of these as our strategic interrogators. We aren't hitting the molecule with a sledgehammer. We are nudging it with inert gas atoms until it begins to vibrate violently. Eventually, that vibration finds a weak point. Here is the forensic precision you need to remember. Bonds break to give the most stable cation. The molecule will always try to fail at its weakest or most strategically important points first. While the stability of the radical formed during the break is a factor, the stability of the resulting cation is what defines every peak you see on your screen. This means that every peak isn't noise. It is a logical consequence of the molecule's architecture. Your job is to understand why the molecule chose to snap where it did. When you understand the why of the failure, you understand the what of the structure. To solve this puzzle, we have to identify the players involved. First, we have the precursor ion. This is our suspect, the original molecule we've selected for interrogation. Then, we have the product ions. These are the clues, the shards generated during the break. When we perform a product ion scan, we lock our filter on the suspect and scan the debris. But one of the most powerful tools in your detective's kit is the subtraction method, or neutral loss logic. Sometimes, the most important clue isn't the peak you see. It's the gap between the peaks. Molecules often lose neutral pieces that carry no charge. Because they aren't ions, they are invisible to the detector, but we can calculate their weight by looking at the distance between the precursor and the fragments. Have you ever seen a mass gap of exactly 18? In my years of consulting, that's an immediate red flag. That's a water molecule. It tells you immediately that your molecule likely has a hydroxyl group. You've just identified an alcohol without ever seeing the oxygen itself. What about a loss of 44? That's $CO_2. You've just found a carboxylic acid. A loss of 17? That's likely ammonia or a hydroxyl radical. This analytical confidence allows you to work backward. Every missing piece is a functional group you can cross off your list until only the truth remains. Now, how do we put it all back together? We look for the scaffold, the central structure that holds the pieces. Think of this as identifying the frame of the car from the wreckage. Different chemical classes leave very specific fingerprints in the debris. For instance, alkanes often show clusters of peaks exactly 14 mass units apart. This is the signature of a repeating $CH_2 chain, the DNA of a hydrocarbon. If you see this, you know you're dealing with a long chain structure. Aromatics, however, have a smoking gun. If you see a peak at mean Fortspars 91, stop everything. That is the benzylic carbocation, which rearranges to the incredibly stable tropylium ion. It is absolute proof that your molecule contains a benzene ring. Amines are equally distinctive. They are famous for $alpha cleavage, which forms resonance-stabilized aminium ions. If your molecular weight is odd and you see this specific cleavage, you've likely caught an amine. Finally, look at your oxygenated species, aldehydes and ketones, which break to form the acylium ion. This confirms the presence of a carbonyl group. Always pay attention to the base peak, the tallest peak in your spectrum. It represents the most stable piece of the puzzle. It is your foundation. You don't build a house from the roof down, you build it from the base peak up. Before we wrap up, I want to remind you why we obsessed over those room-sized FTICR magnets and orbitraps in our earlier modules. When you are a molecular detective, decimal places are your best friend. A nominal mass might tell you a piece of debris weighs 28. But what is that? Is it carbon monoxide? Or is it ethylene? Both weigh 28 to a standard instrument. But with the 6 decimal precision we've mastered, the ambiguity vanishes. You know if it's 27.9949 or 28.0313. High resolution makes your detective work 100 times more accurate because it eliminates the noise of guessing. You aren't just speculating about the identity of the debris, you are mathematically proving it. Molecules don't break by accident, they break by design. Your job is to read that design. Today we've learned the rules of the break, the power of neutral loss, and how to identify the fingerprints of aromatics and amines. You are no longer just operators of a machine, you are molecular detectives. You have the power to find the chemical truth hidden in the debris. But solving the puzzle is just the beginning. The world of industry doesn't just want you to analyze what's broken, they want you to build systems that don't fail. Get ready. In our next unit, Module 9-1, the professional blueprint, we stop analyzing the debris and start building the foundation for robust LC megasiemens per megasiemens methods. I'll see you at the blueprint stage.